Now we're going to start looking at some of these collisions that we can have, special cases. And the first is an elastic collision. And so an elastic collision is one where momentum and kinetic energy are both conserved. And sometimes you'll see this as perfectly elastic as opposed to just elastic. Perfectly elastic collision. And remember, we were talking about elastic collisions here. So something that you'll see that's unfortunate when we move on, but perfectly elastic and elastic are synonyms. They're essentially the same thing. When we talk about inelastic, there is a difference between perfectly inelastic and inelastic. And I'll draw a chart later that'll help kind of clarify it. Anyway, the big idea is momentum is conserved and kinetic energy is conserved. So everything that can be conserved is conserved in this collision. And you'll analyze this by creating and solving a system of equations. One equation will be conservation of momentum. And the second equation will be conservation of kinetic energy. And you'll probably have two unknowns, you'll have two equations, we'll solve it. Let's look at an example. A 70 kilogram ice hockey goalie originally at rest catches a 0.15 hockey puck slapped at him at a velocity of 35 meters per second. Suppose they have an elastic collision, so he's not really catching it, he's deflecting it. Let me change that language. Suppose the goal and the ice puck have an elastic collision and the puck is reflected back in the direction which it came. What would their final velocities be in this case? So let's draw a diagram. So we have a mass of the goalie is equal to 70 kilograms. V initial of the goalie is equal to 0 meters per second. And we have, I'm drawing it big so I can write on it. Mass of the puck is 0.15 kilograms with an initial velocity of 35 meters per second. And then after the collision, we have the puck, so mass of the puck, going backwards in the opposite direction, so final velocity of the puck. And we know the goalie is going to have some sort of momentum change in the opposite direction to conserve momentum. So we have velocity of the goalie is some unknown value. The velocity of the puck is some unknown value. The mass of the goalie is still going to be the same. So conservation of momentum. In this case, I'm going to do final momentum equals initial momentum because that's going to be a little bit easier to work with. So initial momentum is the mass of the puck times the initial velocity of the puck plus the mass of the goalie times the velocity of the goalie initially. That is all equal to 0. And that will equal at the end the mass of the puck times the velocity of the puck plus the mass of the goalie times the velocity of the goalie. Conservation of energy, kinetic energy, is going to be that the change in Ke for the goalie plus the change in Ke for the puck is going to be equal to 0. So this will be 1/2 mass of the goalie times the velocity of the goalie squared minus the velocity of the goalie initially squared It's going to be 0 plus the 1/2 the mass of the puck times the velocity of the puck final squared minus the velocity of the puck initial squared, and that's all got to equal to 0. So now our unknowns are the final velocity of the goalie and the final velocity of the puck, final velocity of the puck, final velocity of the goalie. This is a system of equations with 2 unknowns and 2 equations. What you can do here is just go about solving for one of these variables. So it's probably going to be easiest to solve for, actually probably does not matter a whole lot looking at this. So let's solve for one of these up here because it'll be easier to plug into a square than dealing with a square root. So this expression, we're going to get that the velocity of the puck is equal to the mass of the puck, the initial velocity of the puck, minus the mass of the goalie times the initial or the final velocity of the goalie divided by the mass of the puck. We'll plug that in down here. And we'll get that the 1/2 mass of the goalie, final velocity of the goalie, plus 1/2 mass of the puck times mass of the puck, velocity of the puck minus mass of the goalie, velocity of the goalie over mass of the puck, quantity squared, minus velocity of the puck initial squared. And then at this point, all that will equal 0. We can do a little more algebra here. I can get rid of the 1/2 and just have mass of the goalie. And yes, it is a bit of work when you get into some of these systems. Velocity of the goalie squared plus, let me see, I'm just going to rewrite this for you. Then you can plug in values, rearrange, solve for the final answer. If you want me to double check your work, I can, but for sake of keeping this video short, I want to stop us off here. But you get that velocity of the goalie, and then you can take that velocity, come back up here, and solve for the velocity of the puck. It is a bit of legwork, it is a bit of algebra, but it is just at this point algebra. The important physics step was setting up this equation right here, and this equation right here, and then plugging things in, solving for it, yada yada. These are the most complex that you could have kind of algebraically because it is the one that involves a system of equations and rearranging it.